Hi students, on continuation of our electrical circuits, today we are going to learn resonance in series circuit. In last class what we have seen, if the resistance connected alone to the source, AC source, what is the current, what is the relation between the voltage and current and phase angle and power factor and power. Similarly, if in place of resistance we are connected the inductance, what is the relations of these all things, and if connected capacitor, pure capacitor alone, what is the relations of these all things we have seen. At the same time, we also seen that if combination of some resistance, inductance connected to our AC circuits, what is the relation between the voltage and current and power factor, phase angle and power, and resistance and capacitor if connected in series, then we have seen all these values, and combination of inductance and capacitance in the circuit, then what is the value. All these are we already done some problems also. Now finally we have seen that the resistance and series, inductance and capacitance if we connected across a AC circuit, then what is the final current in the circuit and what is the relation between the V and I, what is the power, what is the power factor and what is the phase angle, and what is the voltage across this and voltage across this and voltage across this, already we know. Okay. So based on that we have done some problems. So very interesting and easy topic also. Step 1, step 2, step 3, step 4, last class we have seen. Here, so there is a one problem here. What is happened here? What we have seen in this circuit, here the XL, L is converted to the XL and that is equal to omega L, that is equal to 2 phi FL. Okay, and C is converted into XC, that is equal to 1 by omega C, that is equal to 1 by 2 phi FC. Okay, we have seen. So these are the things. Now here you can see that X is equal to XL minus XC. Okay, what is that big value? You have to subtract that thing. Okay, here what is happened? X is equal to XL minus XC. That means here XL means that is a depend upon the frequency. Okay, the frequency increases, then XL value also increases. If frequency increases, XC value decreases, inversely proportional. Here you can see F is inversely proportional, here is directly proportional. That is XL is directly proportional to the XL is directly proportional to the frequency, whereas XC is inversely proportional to 1 by frequency. Okay, so these are the two terms. Now what will happen if I change my frequency at input side, where the XL value is equal to XC, one stage it equal values will get. At that condition what will happen? So our Z value, where is the Z? So Z is equal to R square, that is called R plus J of X value. So in this case XL is equal to XC, this what will happen? X is equal to XL minus or this one XC. So what will happen? This becomes the 0. One frequency changed, from low value to the higher value at one frequency, the inductive reactance equal to the capacitive reactance. At that condition, so the ohmic value of inductive is equal and opposite to the capacitive reactance. So this minus this is equal to the 0 value, x value becomes 0. Then so Z is equal, now it becomes to the R plus J of 0. Then whatever the impedance, that is equal to resistance. Okay. So whatever the impedance, that is equal to the Z. So then we can say that, so this resistance occurred when XL is equal to XC. So this Z is equal to R, we can say the resonance impedance. The circuit impedance at resonance frequency is called the dynamic impedance, or we can say the dynamic impedance. Okay. So normal Z impedance, now it is a Z R becomes so dynamic impedance. Okay. So that is the dynamic impedance. Dynamic impedance. So here when it occurred, when the inductive reactance equal to the N capacitive reactance. So at that condition, what is the current? As we know that the current in previous case, so that is equal V by Z. So now it becomes the V by R only. So whatever the ohmic value offered by this X value becomes to 0. Then due to this one, the resistance value, ohmic value decreases. Now the current value increased. So, okay. Now the current value increases. At resonance, what we have seen that, so then what are the phase angle phi r, resultant angle is equal become to 0. So here I is equal V by R, the circuit behaves a resistive circuit, then cos phi, what is the cos phi? Cos phi is equal to unity power factor UPF. Then what is the angle? Cos inverse of 1 is equal to 0, the phase angle also 0. Then what is the power? Power is equal to, so I square R only, or we can write the V square by R. So here we are going to get this all values. So dear students, so when its net reactance is 0, the frequency at which this happen is known as the resonance frequency. The resonance frequency at which our inductive reactance is equal in magnitude but in opposite to the capacitive reactance values. The frequency at which net reactance is 0, if it is known as a resonance frequency. The total impedance is equal to only resistive value. Okay. So in this case, we can say that at resonance, that is the angle becomes to 0, cos phi is equal to unity power factor, and current value increases are very high. And at that condition also we can observe that here, so XL is equal to XC. If I multiply current here, then I am going to get what is the V, voltage drop across the inductive circuit, equal to the voltage drop across the capacitive circuit. This may happen in this case. The voltage across the inductance is equal in magnitude and opposite in phase to the voltage across the capacitance circuit. Then so whatever the circuit here, what will happen? So this is equal to VR, this is equal to, so we can write the X, we can write the V L minus Vc, then it becomes the voltage. So in this condition, at resonance frequency, this becomes the 0. Okay. So here whatever the VR is equal, voltage drop across the resistance equal to the voltage across the supply. Okay. So these are the regarding to the resonance circuit. And at the same time, another term regarding to this one. What is the term? So acceptance circuit. What is the acceptance circuit here? A series resonance circuit draws a maximum current and as well as the power also, maximum power, because I square R from the mains due to the minimum impedance value. This circuit we can say that acceptance circuit. What is the acceptance circuit? A series resonance circuit draws a maximum current and power from the mains due to minimum impedance value. So, at resonance frequency, what is that value, what is the frequency? So, we can calculate that also. Okay. So, what is the resonance at which it occurred? I want to know that. Okay, then a resonance, okay, resonance frequency, I want the frequency. What is resonance frequency? FR. Okay. So, that FR is equal to, so at resonance frequency what will happen? So, XL minus XC, this value becomes to the 0. Then, so what is happen? So, what is the XL? Omega L minus 1 by omega C, that is equal 0. Now, this is equal to 2 phi F L minus 1 by 2 phi F C is equal to 0. Now, what is happen? Here 2 phi F L is equal to 1 by 2 phi F C. Okay. Now, I want the frequency. So, that frequency F, okay, that is F into F, F square, then I can write it 1 by, so 2 phi whole square L C, I can write it. So, here I want the only F. F is equal to under root of this value. So, we are going to get it 1 by 2 phi root is square will go and LC. So, these are the frequency, resonance frequency Hs. So, we can say the FR, resonance frequency. That means, if you know the L, if you know the C, I can easily find that what is the at which the resonance occurred, FR. If you know the FR, so I can set the my circuit. This is the resonance. Okay. So, this is the resonance frequency. Okay, dear students. So, I want to note the at the same time this frequency, what is the bandwidth I required? What is the quality factor regarding to the series circuit? Let us see that is also. Now, bandwidth. Okay. So, what is the bandwidth? Have you learned? Yes, in electron circuits we are listening bandwidth. Bandwidth of a series circuit. Okay, resonance circuit under resonance condition. The bandwidth of a series circuit is defined as the range of frequency over which the circuit currents is equal or greater than 70.7% of maximum current. Okay. So, what is that one? So, let us see. For example, you can draw the one bandwidth. Now, you can take this is a one graph. Here x axis is a frequency, y axis is equal to, that is equal, you can take the current, okay, current. Then here, so the bandwidth of, for example, this is the resonance frequency bandwidth, this is the bandwidth. If the frequency changes, it current value from 0 to increase to the maximum value. At that condition, so when it becomes the maximum, so only Z is equal to R. At Z is equal to R plus J of X, no? So, the X value it changes based on the frequency. Initially, the frequency is equal to 0. At that condition, the inductive values is more here. So, this is the inductive nature, this is the capacitive nature. Okay. Now, once the frequency increases, what will happen? So, inductance value increases. Okay. Inductance value increases, then automatically what will happen? The capacitive value decreases. At that condition, the ohmic value increases. Now, current is also reduced. Sorry, this is a inductive effect, this is a capacitive effect. Because what will happen? If ohmic value increases, the current decreases. Initially, what is the current? This is a current. Okay. So, here what will happen? At that condition, inductance impedance is values more. Okay. So, if go on decreasing, so here frequency is going this direction, so then go on increasing the frequency. Okay. What will happen? So, capacitive value increases, inductive value decreases. So, inductive value decreases, then what will happen? The total impedance decreases. If the impedance decreases, current value go on increasing maximum at one stage. At this condition, whatever the XL is equal to XC. Now, further increases, then this value decreased here. Now, this is the maximum value. If we take that one, okay, this is the maximum value. This is the maximum I max. Now, we are going to the root 3, that is root 2 times, that is a 0.707, that is equal nearly 70%. This is equal to 0.707 I or resonant current, and it touches 2 points. So, we can say this is equal to F1 and this we can say is the F2. Okay. The extreme, the lower frequencies and higher frequencies. Now, in between F1 and F2 is the resonance frequency. Okay. So, these are the two. F1 is the lower cutoff frequency, F2 is the upper cutoff frequency. So, here this is a lower cutoff frequency, this is a higher cutoff frequency. Okay. Now, what is the bandwidth? Bandwidth is equal to F1 minus F2. That means the lower cutoff frequency minus upper cutoff frequency. In between, the frequency is known as the bandwidth. Okay. The bandwidth represents the frequency range at which the circuit offers a low impedance to the circuit. Okay. So, these are the few points regarding to this one. Okay. So, this is a bandwidth. Okay. So, this resonance frequency is lower cutoff, higher cutoff values. So, let us summarize what regarding to this one. What we have seen, one, if the resonance frequency is not centrally located with respect to the lower and upper cutoff frequencies, that is F1, F2, then we can calculate that FR is equal to resonance frequency equal to, we can write it directly F under root of F1 and F2, then we are going to get the resonance frequency. And second point is to remember that if the quality factor of a circuit is greater than or equal to 10 value, the resonant frequency is sufficiently near the center at exactly center here. If two cutoff frequencies, then we can write it. So, what is happened here? So, F1 I want from this one F1 I want to know. Okay, then F1 I can write it F1 is equal to, so total resonance frequency FR minus this is the bandwidth by 2, bandwidth by 2. So, we are going to get this F1. Okay, that means what is the FR up to this area? What is the bandwidth by 2? This area. If total area minus this area, I am going to this frequency, that is called F1. Suppose I want this value, F2 value. So total FR plus this one plus you can add here. So F2 is equal to, that is equal to, so we can write it FR resonance frequency plus you added the bandwidth by 2. Then so we are going to get it. So lower cutoff frequency and upper cutoff frequency. Okay, that is a second salient point regarding to the resonance circuit. Okay, when quality factor is greater or than 10 values. And third important point is the relation between the quality factor and bandwidth of the series resonance circuit. We can write it, the quality factor is equal to, we can write the resonance frequency divided by bandwidth, or we can write it this simply, so resonance frequency is equal to the quality factor into bandwidth. Okay. At the same time we can write it what this one, so that is equal to 1 by 2 phi under root of LC, also we can write it. Okay. These are the resonance frequency equations. Okay. So dear students, what is the bandwidth? The bandwidth of a series circuit is defined as the range of frequency over which the circuit current is equal or greater than the 70.7% of the maximum current. Okay. So the bandwidth BW is equal to F1 minus F2. So mainly the bandwidth represents the frequency range at which the circuit offers a low impedance to the circuit current. Okay. So these are the some regarding to the salient points. Now coming to the quality factor. Okay. So now let us see the what is the quality factor. Q factor, we can say the Q factor or of a series circuit or quality factor. It is defined as the voltage magnification in the series circuit at resonance frequency. At FR, whatever the voltage magnification, that is equal Q, is a voltage magnification. Voltage magnification. The voltage magnification in the series circuit at resonance. Okay. So here at resonance we know that VL is equal to VC and voltage across the LRC is equal to, we can say that. So here voltage across the inductive circuit is equal to the voltage across the capacitive circuit, both are equal, and at the same time we can write it the resonance current and XL, you can take the inductive reactance. Okay. But what is the supply voltage? Supply voltage is equal to, at resonance frequency XL is equal to X0, both are equal, then we are going to whatever the voltage applied, that becomes to the IR, only R. Okay. Then the quality factor, Q factor, we can write it as the Q factor. Q factor is equal to voltage magnification, voltage magnification that is equal, we can write it. So voltage across L or C divided by supply voltage. Okay. So that is the Q factor. It is the ratio of voltage across the inductive circuit to supply voltage. Okay. From this one I can write it the simple equation, dear students. What is that one? Voltage across is a VL and supply voltage is a V. Okay. Then what is the value? That is equal to I resonance current into XL, and this is equal to resonance current into IR into R. This and this get cancelled. We are going to get it XL is equal to here XL by R. Okay, then that is equal to, we can write it omega L by R. Okay, so what is the omega? I can write it, so 2 phi f L by R. Okay, so this is our values. Now we know what is the frequency at this stage, that is equal to resonance frequency. Substitute that value also, then we are going to get 2 phi L by R into what is the FR, that is the resonance frequency, that is equal to what we are 1 by 2 phi root of LC. Okay, then so what is happened, 2 get cancelled, 5 get cancelled. Then I can write it here, so here 1 by R. Okay, so then I am going to institute here L square by LC. Okay, L square will go, then we are going to get it really, so 1 by R root of L by C is the Q factor. So dear students, the Q factor is the quality factor is equal to, if you know the RLC series circuit, that is equal 1 by R into root of L by C, we are going to get it. Okay, the quality factor of a series circuit indicates how many times the potential difference across inductance or capacitance greater than the applied voltage at resonance. Okay, once again, the quality factor of a series circuit indicates how many times the voltage across the inductive coil or capacitor is greater than the applied voltage at resonance. Okay, so dear students, this is the Q factor. So this quality factor and bandwidth, it is a very significant in case of the electronic circuits. Okay, so this is the regarding to the RLC circuits. Okay, so I think you have some idea about the what is the quality factor. Quality factor is equal to voltage magnification factor, we can say it, and at that condition whatever the voltage across the inductive coil is equal to the what is the voltage across the capacitance, both are equal. So that it is taken as a IR into it taken the inductive reactance, or you can take the XC also. So at that condition, what is the supply voltage? So these two voltages are equivalent each other. So that is the XL is equal to XC, then we are going to get it. So whatever the supplied voltage applied across the wholly resistive circuit, this is supply voltage. Then so quality factor is defined as it's a ratio of the voltage across inductive or capacitive circuit to the supply voltage, that is called VL by, so we whatever the value here VL by V is equal to this value we are substituted, then we are going to get the quality factor. Okay, so this is a quality factor of dear students. Now, so I think you have some idea about the what is the RLC resonance circuit, what is the resonance frequency, what is the quality factor if the series RLC connected in series. Okay, so thank you for listening my class, dear students.